Okay, let's get started. Your next homework assignment's due on Tuesday. I think I forgot to eliminate homework 5 off of your notes, so you can cross that out. You've already submitted homework 5. Homework 6 is due next Tuesday, and also next Tuesday we're going to have the first exam. I've just given you the equation packet, which is version 9.1 of the FE supplied reference manual. In the actual FE, they give you that digitally. You can't take the paper copy of that handbook in, and so the advantage is that you can search by keyword, whereas previously, even if you looked in the index, some things, like very common phrases, you'd search for it in the index and it wouldn't take you where you needed to go. And so in some ways it's less critical than it was before to know in advance where everything is. What's still really important is to be comfortable with the forms of the equation that they provide. Yes. Yes. Yeah. So the exam's going to include through today's lecture, and not the project. The majority of actually what we'll spend time on today is the project, but there won't be any questions related to that on the midterm exam. You can use the equation packet that I've just given you, and then one other sheet of paper, letter size, 8.5 by 11, front and back. You can put anything on it you want. Bring your computer if you'd rather use that instead of one of the tablet PCs. And as I've mentioned before, you will probably have an opportunity to use Excel. And when you do, you can't use an existing file. You have to start with a blank worksheet. Anything you want. That's right. Yeah. Front and back, yeah. And side. You can write along the side as well. Yeah. All right. Any other questions? All right.
Over the week, we email you to see if our answers on homework are correct.
Yeah. Yeah. I love those little weekend presents. It reminds me that I've got students working hard. While I'll be boiling maple syrup this weekend. I've been collecting maple sap. I have maple trees on my property, and I've got about 50 gallons that I need to boil down. So I'll be occasionally running from the woods. Check my email, see if there's any questions, and I'll run back to the maple. All right? Maybe I'll bring some in. We can all pass around a flask and do maple shots, right?
There we go.
All right. During the exam. Get the creative juices flowing. All right. Some of you have mentioned that you're having a hard time translating what we talked about in class Tuesday into the homework problem, like seeing the connection. And the big idea from Tuesday's lecture is set the system curve equal to the pump curve and solve for Q. And so sometimes the challenge is constructing the system curve. And I presented the formula for how you can write the system curve, the equation. Let me see, we can get back to that. Here's the system curve equation, the general form of it. And so the general form of the system curve equation says, look for the elevation difference between two reservoirs, or between the origin and destination. So the delta Z, Q will be unknown. That's what you're going to be solving for when you set the system curve equal to the pump curve. FL divided by 2G A squared D. Now, F in one of the problems, it's called, they say, the friction coefficient, something like that. Who was it that asked me that question? How did they phrase it in the problem statement? Coefficient of friction. And so in that particular problem where they say the coefficient of friction is, and they give you a number, that's the F value. So you're not having to actually find it in that particular problem. L is just going to be the pipe length between the origin and the destination. And even if it's submerged pipe length, you still have to account for the entire length of pipe, because even a submerged pipe induces friction. So, these two pipe lengths, even though they're submerged, the water comes in here and goes out there. And so if the entire length is 50, that's what you've got to use as the entire length. Okay, so this part of the term is pipe friction. This part of the term is related to local losses. And so K naught is the sum of all of the local loss coefficients. And so in a case like this, if they don't tell you any information about the bends, if you don't have a K value for a bend, what you can still do is use the K values for the entrance and the exit. And in your book, it tells you which coefficient you should use for a pipe entrance. If it is like a flush with the wall, it tells you that would be like a 0.5 for an entrance like that. If it's rounded, then the K value is a little bit lower because it causes less turbulence. If the pipe extends into the reservoir like this or like that, then the K value is 1.0. And then anytime you have water discharging into a tank, K is 1. And the reason for that is you think about you have some velocity head. There's energy tied up as velocity head as the water's flowing through the pipe. As soon as the water exits the pipe and goes into the tank, all of that velocity head is instantly lost. And you'll remember that when we talked about hydraulic grade lines last semester, we had, and energy grade lines, we had the energy grade line, a hydraulic grade line, and if we had a tank of some sort, here's the water surface. At the end, the EGL was above the water surface, and the HGL stopped at the water surface. And so this V squared divided by 2G, the magnitude of the energy grade line above the hydraulic grade line, that's an energy loss. And so the K value you should use for an exit is 1. And for an entrance like that, the K value is 1. So I just wanted to emphasize that in each of those homework problems, maybe they're not telling you specifically what the system curve is because you're having to interpret the drawing and create your own system curve. And in one instance, they don't tell you the pump curve. And instead of being given an equation like that, instead of being given the formula, they give you curve. And so remember that this graphical curve, the 24.4 in this equation, refers to the shutoff head. And so that if you were given the curve, you would say HP equals, and then whatever the intercept is, the y-intercept at q equals 0, would be that first term, and then minus some factor times q squared. And so you need to plug in a few values to find the correct factor to use for that coefficient that's before the q squared. Any questions that have come up that you want to ask about briefly before we move into some extra things about pump operation? All right. Well, with that, let's take a look at this example. We've got water pumping from a lower reservoir. We've got a delta Z on the suction side of 1.5 meters. And the head difference from the water surface at A up to the discharge location at C is 12 meters. We're given the pipe length and an F value. If we weren't given the F value, then we'd assume the fully turbulent flow assumption, and then later on we'd check it. But things are simplified a little bit. So let's just get a little bit more practice on this. We want to find out how long it's going to take to pump a metric ton of water. How many hours? In other words, we're going to have to find the flow rate, and then we're going to, once we know the flow rate, find out how long it would take to pump that metric ton. And then the second part of this example, we'll take a look at the implications of efficiency. Okay, given already is the pump curve. And so the pump curve is H equals 18 minus 5.6 Q squared. And that's even too sloppy for me. 5.6. All right, system curve. We're going to generate one ourselves. The system curve essentially is just the energy equation. So let's start with it that way. All right. So at location A is going to be 1, and location C is going to be 2 in this formula. There's no pressure here. We're going to let this water surface at A be our elevation datum. So that makes Z1 equal to 0. And there's no velocity head at the water surface there. So HP is what we want to find out how much pump head is required to add. And now the pressure at 2 is 0 because you can see that's discharging into a jet. So on the outside of the pipe, once the water comes out of the pipe, it doesn't have any pressure anymore. But it's going to have an elevation, Z2, of 12 meters. All right. And now we have to take into account the velocity head there because it still will be moving. So we're going to have an unknown velocity, v squared divided by 2g. And actually, we're going to use the Q version of velocity, where instead of v squared divided by 2g, we'll say q squared divided by 2g a squared. For our purposes, that'll be a little bit simpler because the head losses are also going to be expressed that way. Now, there's two components of head losses. There's going to be the friction losses and the local losses. So in this instance, we have an inlet loss of 1.0, so it'll be plus 1 times the velocity head, q squared divided by 2g a squared. And this is local loss. And we also need to put in the friction losses. And the friction loss here, it's going to be FLV squared divided by 2g d2g, and we'll put that also in terms of Q. So the friction losses are going to be 0.021 F, now times our L, 135 meters, Q squared, divided by D. And in this case, we're given that the diameter of the pipe, I haven't started substituting in all the values yet. I'll continue with the numbers here. So the diameter is 0.1 meters, D, 2G, 9.81 meters per second squared, and then A squared. And the area, pi D squared divided by 4. I don't have that written down here on the page. Can someone calculate the area quickly? And then we'll substitute that value in each of the places where it's found. 7.85. Okay. So A squared, where we've got the 0.00785 meters squared, and square that. Okay, so this was our velocity head. This is the inlet local loss. And so the pump is going to have to apply 12 meters of head just to lift the water. And then it's going to have to add enough head for it to have velocity. And then also the local losses from the inlet. There won't be an outlet loss because the water is still moving as it comes out of that orifice. And then here is the coefficient for our friction losses. And so that gives us an HP. Actually, I need to calculate that because I've made some changes to this example since I had it in my notes. So we'll go through together and calculate that. Okay, so we have the area of point 00785 squared times G 9.81 times 2, 12 meters plus 0.00121 q squared plus another 0.00121 q squared plus, now this term, 0.021, 135 meters, 0.1 is the diameter, 2 times 9.81. And double check my calculations. I could be messing things up here as I do it on my phone. I appreciate the double checking. $23,448.483 q squared. So should it be this?
Yeah.
Yeah.
Supposed to be Q squared.
Right, well, q squared's in the numerator. Yeah, okay. Yeah, I forgot to do the inverse at the end. All right, so 0.00121. So it's 826. Is that what you got? 0.4? 826.4. Okay. So if we add everything up, 826, two of those, 23,448.483. That's all right, so H sub P is 12 plus 25,101 times Q squared. So that's going to be our system curve. So now we need to set our pump curve equal to our system curve and solve for Q. Okay, so we had 18 minus 5.6 q squared is equal to 12 plus 25,101 q squared. All right, so it's going to be 6 over here, adding 5.6 to that side, 25,106.9 q squared, and then we divide that by 6, no, other way around, 6 divided by that, and the square root. So Q should be 1.55 times 10 to the minus 2 cubic meters per second. Okay, so that's, if we multiply that by 1,000, that's approximately 15.5 liters per second is what's going to be the flow rate there. So it's asking how many hours will it take to pump a metric ton? And a metric ton is 1,000 liters. So 1,000 liters, and if we're doing it at 15.5 liters per second, it's not going to be measurable really in hours. It's only going to take 64.7 seconds So in terms of hours, if there's 3,600 seconds in an hour, it's going to be 1.8 times 10 to the minus 2 hours. Okay. Yeah, because a metric ton is 1,000 kilograms, and a kilogram is the mass of 1 liter of water. So there's 1,000 liters in a cubic meter, and a cubic meter is a metric ton.
You just worry about the length of the suction side.
Cavitation. When you're doing the NPSH problem is when you're focusing only on suction side. Good question, because last time we were looking only at the delta ZS. And so in this figure could be used also for a cavitation problem, which is why they separately called out what the suction side length elevation difference was. Was there another question? All right. So the second part of this was dealing with efficiency. So if the pump is 80% efficient and the motor is 65% efficient, how much power will be consumed by the motor in watts? Okay, we first need to find the overall efficiency. By the way, how many seconds was that we just calculated? 64.7 seconds. All right.
What is that?
It's a 6. Isn't it a G? It looked like a G, but it was a number 6. All right.
That makes so much more sense.
Yeah, it does. Yep. Often the likely thing is the case. Yeah. That would be the Yeah, exactly. Yeah. So the delta Z that was given here was the water surface to the pump, to the center line of the pump, most probably. But if we were doing a problem where we were calculating the net positive suction head, then we'd be interested in the elevation difference just from the water surface to the pump itself. Yeah. Uh-huh.
So that's just extra information.
It is, because I think this drawing's used for a number of different problems. For what?
Go with 12 plus 30. Is that 25,000?
23,448. This one right here? Yeah, 25,101. If you add 826, 2 times 826 plus that, it won't be 30,000. Okay. Yes?
So on that drawing, if you were to put a point where point 1 and point 2 are, would
Yeah.
point 1 be right at the entrance?
Good question. No. Point 1 would be right here. And the reason why I say that is, remember that we said that the pressure at 1 was 0. And the pressure of the water at the surface is the same as the pressure of the air. And so the air pressure in terms of gauge is 0. So if I wanted this to be location 1, then I would have had to actually calculate what the water pressure is there.
You still use the length of the pipe.
That's right, because you go, if this is 1 and that is 2, then you have to think about what's the route from 1 to 2. How much pipe length is between them. So the water that starts at 1 and ends up at 2 is going to have to go through that entire pipe distance. Other questions? All right. So efficiency. We need to find the overall efficiency, and we can do that .8 for the pump and 0.65 for the motor, and that gives us a combined efficiency of 0.52. Okay, the power equation, power is the flow rate times the unit weight times the pump head. All right, and so we said that our flow rate was 1.55 times 10 to the minus 2 cubic meters per second. The unit weight of water is 9810 newtons per cubic meter. And then the pump head that's required, we need to substitute back into one of these two equations, either the system curve or the pump curve with the flow rate that we've got, because we actually didn't yet calculate what the pump head is. And so let's do that. The pump head, H sub P, is going to be 18 minus 5.6 times Q squared. All right. So back to the calculator. 18, 5.6, 0.0155. 17.99 meters of head. So the flow rate's very, very low relative to the head that this pump is putting out. So we can substitute in the 17.99 meters of head that's being added by the pump. And so now we need only multiply those three terms together, 0.0155 for the flow rate, 9810 for the unit weight, and the 17.99 for the pump head. And we get that the power is going to be 2737 watts, but that would be if it was 2737. We haven't yet accounted for the efficiency. So we know that the efficiency is 0.52. So let me ask you, do we multiply by the efficiency or do we divide by the efficiency to find out how much electrical power is consumed? If this is the perfect case, if this would be if efficiency was 100%, it would take 2737 watts. So is it going to consume more electricity or less electricity than 2737 in reality? More. So we divide by our efficiency factor. And so the power required is going to be 2737 divided by 0.52. 5,263 watts. All right. So that's how much power is consumed. All right. Any questions before we move on?
Yeah, but would you use the system curve to get that Q value?
We could. Excellent question. I was going to mention that you could use either the system curve or the pump curve, and you're going to get the same thing. So let's just prove that to ourselves. The system curve, if we had substituted into the system curve, then it would be 12 plus 25,101 times the Q squared, 0.0155 cubic meters per second. Let's just find out what the pump head is. 0.0155 squared times 25,101 and 12, 18.03 meters. The difference being round off. We were 17.99 over there, 18.03. Good question. All right. The next thing we're going to learn about are called affinity laws, sometimes called scaling laws. And actually, there's a series of equations in the FE packet that I just gave you of the affinity laws. And what they're related to is the fact that sometimes manufacturers, rather than starting from scratch every time they design a pump, they'll use a similar shape, but they'll just scale up the size of the impeller and the pipe housing. And so they'll have these related pumps that are maybe a similar shape and performance, or sometimes what you'll do is you'll have a pump but you'll operate it under different conditions. What these affinity laws allow you to do is allow you to compare the performance of a pump under one situation with that same pump under different circumstances. And so for these variables that are defined here, volumetric flow rate we already know about, mass flow rate we already know about, head here, what we're calling H on this page, we've been calling pump head on the examples we've been doing. So you can put in parentheses here that this is really H sub P. It's these are pump analogies, and the pump head is what we're talking about. P, pressure rise, is how much added pressure is being added by the pump in question. Power, W dot, is the term that the FE manual gives to power, and that's the P that we just solved for here in this equation, how much electrical power in terms of watts. And the reason why the units aren't provided here is because you can do these in either BG units or SI units. Density of the fluid. Now, rotational speed is the only one that I think we really need to emphasize. And the rotational speed that they're talking about here is how many radians per second the pump is turning. Sometimes it doesn't matter if you use the right units because, you know, whatever, if you use RPM on one side for this one, RPM versus RPM, it's going to be the same. But when you start squaring terms, then it's important that the units be expressed correctly. And so technically it's radians per second that those pumps are in, the rotational speed. And then the impeller diameter is talking about the, for a circular shape of the impeller that's inside of that pump, the outer diameter of that circular shape. And so what these affinity laws allow you to do is, it's sort of like when we were doing dimensional analysis, or when we were comparing the performance of a prototype and the performance of a model. You'll remember that we talked about the Matchbox car and how it's unusually strong because of its small size, and so it actually behaves as a poor model for a full-size car. You know, a full-size car will dent if you back up into a curb at 5 miles an hour. But if you scale down that collision to a Matchbox car, the Matchbox car doesn't actually dent in the same way that a full-size prototype would. And so, you know, that's a bad analogy, the Matchbox car to a full-size car. So the same kind of mathematic principles that we were talking about in dimensional analysis and Chapter 8 from last semester, this is what this is picking up on. And it allows you to basically look at pumps and how they behave in different circumstances. And so just an example of how problems like this work. If we had a pump that normally spins at 1200 RPM and it's got an 8-inch diameter impeller, and we're given the performance curve from the manufacturer, what if we use that variable frequency drive that I talked about last time, where you're actually changing the frequency of the electricity from 60 hertz to something else? What if you use a VFD to get that to spin at 2400 RPMs instead? So we want to use these pump laws in order to find out what the performance curve for the modified rotational rate will look like. So for this first one, I'm going to work over here on this board. We're going to be changing the rotational rate from 2400 to, I'm sorry, from 1200 RPM to 2400 RPM. And so the performance curve first of all, we'll look at the rotational rate. For 1200 RPM, how many radians per second is that? Do you remember what the conversion between RPMs and radians per second is? Remember, there is 2 pi radians in 1 revolution, and there's 60 seconds in 1 minute. So how do we convert from RPM to radians per second? Multiply by 2 pi to get the radians per revolution, and then divide by 60 seconds per minute. Right, yeah, that's it. Okay, so we want to take the 1200 and the 2400, 1200 RPM times 2 pi divided by 60. Okay, so that is 125.7 radians per second. And then the other rotational rate that we're going to have, so this is N1, the rotational rate in the first instance, and the rotational rate N2 is going to be just double that. So it's going to be 251.3 radians per second. All right. We're going to have to use both of these equations to find out what the new performance curve looks like. And so the first analogy is Q1 to N1 is equal to Q2 divided by N2. And I think that the reason why we're doing that, you'll notice that diameter is one of the terms, but in the description of the problem, it doesn't say anything about changing the diameter. It's the same pump from case 1 to case 2, so the diameter hasn't changed. So D1 equals D2, so we're going to be omitting it. Or D1 equals D2, which is what you do when it's the same pump just being used under different conditions. So we can rearrange that and express Q1 in terms of Q2. So that is going to go to Q1 is N1 Q2 divided by N2. Okay, so that is the N1 was 125.7 radians per second divided by 251.3 radians per second times Q2. Okay, so Q1 is just basically 0.5 Q2. Now the second equation that we're going to use, we're going to substitute in the head, and the diameter is the same. So our second equation is going to just simplify to h divided by the rotational rate squared. So h1 divided by n1 squared is equal to h2 divided by n2 squared. And this is where, again, D1 equals D2, since it's the same pump, just spinning at a different rate. Okay, so that works out to H1 is N1 squared times H2 divided by N2 squared. All right. So we've got the 125.7 radians per second times H2. So H2 divided by 251.3 radians per second squared. And that is going to be 0.25 H2. So H1 is 0.25 H2. Now, we were originally given the performance curve for the pump was H1 is 12 minus 0.1 Q1 squared. So under the conditions that are described in situation 1, this is the performance curve. So the head that's generated at situation 1 is 12 minus 0.1 times the flow rate that is going at situation 1. But we want to find out what happens if it spins at the other rate. So we're going to substitute in this H1, H2 relationship and this Q1, Q2 relationship. And so under the new conditions, so this was at 1200 RPM. Now if we want to find at 2400 RPM, then we're simply going to substitute in 0.25 H2. So we're substituting in where we had this H1, and then we are going to still have 12 minus 0.1, and then substitute in 0.5 Q2, where we had the Q1 before. So ultimately what that leads to is H2 is 48, because we've got the 12 divided by 0.25 minus 0.1 Q2 squared. So this is the new performance curve for the pump at 2400 RPM. Pump performance curve. Kind of a strange process, but it allows us to predict how that pump's going to behave under the new circumstances, so it's useful. Instead of generating 12 meters of cutoff head, it's going to generate 48 meters. And so we've essentially quadrupled the cutoff head by doubling the rotational speed, and then we lose head at the same rate as we did before, 0.1 meters of head for every cubic meter per second of flow rate. Yeah?
On the previous slide there,
Mm-hmm.
you had pump head, or where is it at? Yeah, head, pump head is equal to H.
Yeah.
Water diameter is equal to H.
Where's that?
Right there. Is that supposed to be?
Oh, that's supposed to be D. Thanks for noticing that. Sorry. I copied and pasted these three terms, but yeah, that should be D. I'm glad you noticed that. So will everybody please change that in your notes here on the previous slide where it said H was impeller diameter. That's actually supposed to be D. Good catch. Other questions? All right, well, let's move on to the second part of this example and find out what if it's still the original 1200 RPM, but we switch to a 10-inch diameter instead. All right? So let's see. Originally used an 8-inch impeller. D1 is 8-inch. D2 is going to be a 10-inch. And we're still using the N1 is going to be 1200 RPM. And N2 is also 1200 RPM. So what's going to be the modified performance? Yeah, we use the original 1200 RPM motor, but we want to switch to a 10-inch impeller. Then what's going to be the modified pump performance curve? Okay, so they are. Yeah, on the second part of this example, we're switching from the 2400 back to the 1200. So they're the same. Okay, so what we have is Q1 divided by D1 cubed equals Q2 divided by D2 cubed. And then we're also going to have to use H1 divided by D1 squared is equal to H2 divided by D2 squared. So these are the two that we're going to be substituting things into. Okay, so Q1 is 8 inches cubed, because that was the diameter of the first pump, times Q2 divided by the diameter of the second pump, which is the 10-inch diameter, cubed. That gives us Q1 is 0.512 Q2. And now, making the substitutions here, we have that H1 is 8 inches squared divided by 10 inches squared times H2. So H1 is 0.64 times H2. So if we substitute both of those into the original performance curve like we did before, so instead of H1, we're going to have 0.64 H2, and then we'll have 12 minus 0.1 times Q1, and instead of Q1, we'll substitute in 0.512 Q2 and square that. Then H2 is 18.75 minus 0.04096 Q squared. All right. So this is the pump performance curve with the larger impeller diameter. So pump performance. So what advantage is there with going with the larger impeller diameter? You know, if you're comparing, let's say that you have the option of either keeping the pump and increasing its rotational speed, or keeping the motor, which is what spins the pump, and increasing the pump impeller diameter from 8 to 10 inches. What's the relative benefit of each of those moves? Like, in what case would switching to the faster rotational speed be better?
If you need a higher shut-off head.
Right. If you're pumping to a higher elevation, then the higher rotational speed is better. The second case that we looked at, you have a little bit higher pump head. You know, it goes from 12 to 18. But the real benefit is if you look at this, it was 0.1 before, now it's 0.0409. What that means is that instead of losing pump head at a rate of 0.1 meters of head for every cubic meter per second, now you're only losing 0.04 meters of head for every cubic meter per second. And so the advantage of this larger diameter impeller is just that as the flow rate increases, it loses its pump head more slowly. So if you were going to go with a high flow rate, then the larger diameter impeller would be the way to go. If you're going to be pumping to a higher elevation, then it would be better just to increase the rotational speed. All right, introduce project. That I can do. I'm going to first give you a map. And this map has been posted online along with instructions on how you can import it into WaterGems.
What were the benefits of the large impeller?
It loses head more slowly than the yeah. Well, no. If you had a higher flow rate, it would be better for a high flow rate. It does look familiar, right? Okay, I've given you the map, and what you're looking at is a hypothetical town that is, it doesn't really exist, but it's on a hillside, and those contour lines give you an idea of what the elevation profile is like. So the elevation is high on the northwest part of town, and the little symbol that's by the 300, it looks like a sort of an X with a line through it. Spider. That is where a spring is located. That's the source of water for the town. As they get the water off of that spring and then they pipe it into the town, and the water enters at A. The water goes into the network at A. And the image that I've provided online, actually, let me pull it up. It's in color, and the colors actually have a significance. There's a new folder in here that's called Design Project Items, and in addition to the image that I've given you, there's some other things as well here that I'll tell you a little bit about in a minute. Let me save that image and then open it up. All right, so the blue lines are pipes. The green lines are where water comes out of the pipe network and goes into the town. And what you're going to have to do in this project is in phases go through the design process to try and decide how big each one of those pipes needs to be. And as with your previous efforts, remember the objective is to minimize the pipe diameter. You want to give these people the smallest pipe network that's going to satisfy their needs, because pipes that are any larger than the smallest possible pipe network are unnecessarily costly. So this project goes through in a couple of different phases. The first thing you're going to do is demand forecasting. And I've made assignments that I'm going to hand this out in a second, but you'll go through the second to last page and look for your name. And for example, Andrew has Reno. Each of you has been assigned a city, and then there's a series of assumptions I want you to make about the population density inside of the city, the fire flows that are needed in case there was a fire that the fire department was going to be taking water out of the pipe network to fight. In the list of assumptions I tell you, there's a hotel in Loop 3 and how many guests the hotel can be expecting at peak capacity. There's a food plant in Loop 3 that's described in the handout, and so I tell you how much water is being used by the food processing plant, and there's a shopping mall inside of the loop that also requires water. There's a sports stadium here, and in the assumptions I tell you how many people there are, actually how many seats there are at the sports stadium. For this box factory, I tell you each one has different numbers, the size of the square feet of the box factory and how much water they're demanding per square foot. There's a hospital over here at K, you can see, and so I tell you about how many beds they have in the hospital, and for this high-density housing project, then how many units there are, and there's a golf course not shown. There's a pipe coming off to provide irrigation and other water for the golf course, and so I tell you how many acres they've got. And so the first phase of this project in demand estimation, what you're going to do is use both the references that I've provided and your own assumptions and information you find online to try and determine how much water is required. And so here in the reference information that's available, for example, you can see how much water is used for irrigation in different places. You can see industrial uses for commercial areas. You know, how many liters per second per person there is in a commercial area. Or for domestic demand, you know, in residential areas, what the water demand is. There's a table that provides information on what that water is used for, you know, how much goes to toilets, drinking, washing, and so on. Here's information about commercial facilities, including hotels and hospitals. So in these references, there's some information that will help you during demand estimation. And in part of it, you're going to have to go to Google, and for example, on the golf course, I tell you that what you should do is provide enough water to irrigate the grass at the golf course And so you need to know how much rainwater there usually is. And you can assume that a golf course uses 1 inch per week. I think I say in the handout that you need to assume that there is 1 inch per week provided for the golf course to irrigate the grass, and then once you do some research on how much rain there is in the area, you'll know how much balance you need to make up with the pipe network that's there. So the first phase is demand estimation. In the second phase of the project, what you're going to do is build a pipe network, just draw out the location of the pipes. And for this one, I would like you to do it to scale. Previously, when you've done water gems, we've sometimes done drawings where the drawing was just schematic, and so where we clicked on the map didn't really have any relevance to how long the pipe was. But here in the import instructions, I just give you some information on how you can import the image that's provided. It's a very specific size, and each pixel equals 1 meter on the image that I've provided. So when you import it to scale, then you can click at these different junctions, and then it'll make the pipe the correct length based on where it's drawn. So you'll be importing the image in the background and then drawing the pipe network on top of the location where each of those blue lines is indicated. The third phase of the project is going to be to size a reservoir. And I'll teach you the design process that's used for finding out how big the tank should be if people during the day are going to be using a different amount of water than they use at night. There's a process of applying peaking factors. And when I teach you about reservoirs, I'll bring this figure up again. I'll ask you to digitize this figure so that you can use it in your use it in your reservoir sizing. But what this figure illustrates is that during the summer, for example, on the day of the year where people are using the most water, on the maximum day of the year, that the demand for water at 8 p.m. is much larger than the demand for water at 2 a.m. And so why do you suppose that is? Why is there this wide swing in the demand for water over time?
People are asleep during the night.
Yeah, people are asleep and not using as much water at night as they are at 8 p.m. where people are taking showers or washing clothes or doing dishes, that sort of thing. So this is what's called a temporal distribution, where the intensity of something varies over time. That's the definition of a temporal distribution. So we'll have a class period where I spend some time teaching you the procedure for designing a reservoir, and a big part of it is understanding people's water use patterns. Because on that map where I pointed out there's a spring up in the hills, that spring can't turn up and turn down to satisfy water demands. There's a continual flow of water out of that spring that doesn't vary, and so you have to have a water tank to make up the difference between how much is coming from the spring and how much people are demanding at different times of the day. And then the last element of this project is to come up with a cost estimate. And that's actually relatively straightforward because you're going to know what size of pipe is required for each one of the... That didn't sound good. You're going to know how big each one of these pipes need to be, and you're going to know the length of each one of them. And so I've given you a table in the assignment that says the cost per meter of pipe, and then also some information on pricing the reservoir that you're going to specify. In previous semesters, I asked students to do some engineering economy and the time value of money and finance the project, but I've eliminated that. That's maybe just a distraction from the hydraulics that I prefer that you focus on. So let me give you a couple of minutes to read through that assignment description silently. That'll give me time to hand back your quizzes, and then I'll see if there's any questions or any points that you want to have clarified. Instead of everything being due all at once, I am asking you to submit things in phases, and there's a number of benefits to that. First of all, it helps you to avoid procrastinating. And so it's a little bit of an encouragement to break this up into manageable pieces. And the other benefit is I get to give you feedback along the way. So on Thursday the 6th of March, you're going to turn in your demand estimation, and I have some values that I consider in the ballpark. I've done the calculations for each one of you, and it was a spreadsheet. It was pretty easy. I'm not going to show it to you, but it's like my answer. There's no real right answer because a number of these things are related to judgment and assumptions, but I know the ballpark for what it should be. And so if I think that you've been too high on the golf course or too low on the housing development, then yeah, I'm going to give each one of you feedback at each stage. So Thursday, March 6th, when you turn in your demand forecasting, within a week, I'll be able to give you some feedback. And in the meantime, you're going to be working on the pipe network sizing. And so you can draw the layout of the pipes and start optimizing them even before you have your final information on the demand. Of course, the thing that you're going to be submitting under the demand forecasting is calculations that summarize your demand estimation. And those can be hand calculations. In fact, sometimes students are trying to be extra neat, and so they'll like type up their calculations, but that seems like a lot of extra work, and it's not any easier for me to understand if you decide to do it by hand. Or if you want to do it on Excel, that's okay too. But I just wanted to emphasize that for the demand forecasting, I'm perfectly happy to get your calculations by hand, assuming that your hand calculations are neat. An important thing that I mention is that when you get into the design phase, there's two conditions that you need to know the flow rate estimates for. And one of them is the maximum hourly flow. And by that, what it means is for the peak hour of the peak day, so the hottest day of the year at 8 p.m., what is the flow rate that's being consumed in terms of liters per second at the peak hour of the peak day? That's one condition. And then condition two that you have to compare is compare the maximum daily flow, so that means the average daily flow rate during the 24-hour period that is the maximum day of the year, plus the fire flow that I've specified. So you have to compare and find out which of the two is larger. And if you go to the final page of this, the demand forecasting summary table, this is something I put together a couple of years ago to make it easier for students to understand how peaking factors are applied and how some things aren't peaked, and basically just what the two design conditions are. So the peaking factors, I can tell you right now, is that the peak day versus average day, the peaking factor there is 1.8, and the peak hour to the average day is 3.25. And I don't remember if I say that explicitly here or if it's just something that we'll go over later. But the peaking factor for the peak day to average day is 1.8, and peak hour to average day is 3.25. So that gives you a pretty good idea of what you should be doing just to get started. You should be doing the calculations you need to fill in this final page here. So look at your assigned city, and for the population density, how many people are in loop 1? How many people are in loop 2? And based on your engineering judgment of the demand per capita, and that's something that the PDF reference I've given you will tell you how many liters per second per day, how many liters per second per person is required. HA is a hectare, and that is 100 meters by 100 meters. So it's 10,000 square meters is a hectare. Good question.
What's the difference between this, like it says Loop 1 residential and
NFF is the fire flow. And so I just tell you straight out how much water you need to budget for a fire. But what I don't tell you is how much water the people inside there are going to be requiring for their ordinary domestic demands. And so that's what you're going to have to calculate. And in loop 2, there's both residential and, let's see, I guess there's just commercial stuff in loop 2. Residential, yep. Commercial. Loop 2 just has commercial and fire flows. All right, the image that I've given you is the printout, the big 11 by 17. This line on here is 1 centimeter, and that is 100 meters in real life. So that gives you an idea of the scale. So if you're trying to find out what's the area of loop 1, you can just measure it and find the overall area.
So that line would look to 100.
100 meters, yeah. 1 centimeter is 100 meters.
So when we're trying to calculate what the demand at each one of those points is, how do we split the flow between the
Yeah,
two?
yeah, exactly. So you'll notice that there's 2 green arrows feeding the flow into loop 2. So you'll find out the total water that's required in loop 2 and split it evenly between the 2 loops that feed it, the 2 inlets that feed it.
Those numbers that you were given earlier, what were they for?
1.8 and 3.25. You'll notice on the summary table that, let's say that your residential demand was 100 liters per second. Just for example. The 1.8 would mean that if your average day is 100 liters per second, then the average of the peak day would be 180 liters per second. And so the peaking factor tells you the ratio between the peak day and the average day is 1.8. And then the peak hour to the average day is 3.25. And so if your average day flow rate is 100 liters per second, that would mean that the peak hour, the flow rate, the peak hour of the peak day, the flow rate demand is going to be 325 liters per second. Okay. I'm sure you'll have lots of questions come up, and we'll have a few minutes at the beginning of each class to talk about the project and clarify any uncertainties you have. But the whole objective of this, number 1, is to get you a little bit better at water gems. And secondly is to make you more comfortable with the design process, and specifically that sometimes designs proceed with assumptions and guesses that you'll have to clarify and improve down the road. All right, with that, remember that we have our exam coming up next Tuesday, and we won't meet again before that. So what you should do is work on that homework assignment. Let me know if you've got any questions. Send me those emails over the weekend, and I'll do my best to respond, and also do my best to get you your homework back to you before the exam. But then prepare the equation sheet as well. You can bring 1 page with whatever you want on it. All right, see you Tuesday.